Hello everyone, my name is Nikita Umerov, and for the last few years I've been thinking a lot about what an integral is. Because if you can't explain something to a child, you don't really understand it yourself. Recently I finally understood what an integral is. I wrote an article about it, and it got quite a lot of downloads for this kind of publication. You can download it via the link in the description and check it out if you're interested. Don't worry. In this video, I will explain in simple terms what an integral is. For that, an elementary school level of preparation is enough. I will also show you the proof of the Theorem 2 from the article. This is a key result. It requires some effort to understand, but I will provide all the necessary concepts, so you can consider this is a video for dummies. Let's begin. In mathematics, there is the concept of distributivity, which is also called the expanding brackets rule. Suppose you have two operations, for example, plus and multiplication. Plus and multiplication. We say that multiplication is distributive over plus if the following rule holds. A plus B times C equals to AC plus BC. Technically, this is called right distributivity, because C stands here on the right. If C would stand on the left, that is, C A plus B would equal C A plus CB, we would say that multiplication is left distributive over plus. When multiplication is commutative, that is, for all AB, we have AB equal to BA, left and right distributivity are equivalent. You can check this yourself. But in this video, I will use only right distributivity. Alright, now we have everything to define an integral. According to our definition, an integral is an operation over which another operation is right distributive. In other words, here plus is an integral over multiplication. So integrality is just a relationship opposite to distributivity. That's it. Now you know what an integral is. In the article, there are several examples of integrals. The ordinary sum, so-called Lebesgue integral, and probably the most important example is the antiderivative, the integral familiar to everyone from university and high school. You're probably trying your best to forget it, and I understand you perfectly. But today I'll try to convince you that it's not so bad after all. The antiderivative is denoted like this. Integral sign f dg, where f and g are some real-valued functions. The point is, there is an operation of composition between functions. It usually denoted by a circle. F circle g. It turns out that the composition operation is distributive over the antiderivative in the following sense. If we take the composition of the antiderivative with some function h, it equals integral sign f composition h d g composition h. This is called the variable substitution rule, but in fact it's simply the distributivity of composition over the integral. If this video sparks your interest, I will make a separate video about what functions and composition are. For this video, I consider functions simply as objects and composition simply as an operation that takes two functions and returns a third. Today, what is important for us is only that composition of functions is also distributive over multiplication. We have multiplication of functions if the functions are real valued, and the brackets expand as follows. F times G, composition H equals F composition H times G composition H. However, if you came here only to find out what an integral is, I have nothing more to tell you. Now you know what it is. And even three examples of integrals: sum, antiderivative, and multiplication of functions. So you can sleep peacefully without fear of the variable substitution rule. But for those who watch the video to the end, I will show you the main secret. It turns out that all distributivities work in the same way, and the antiderivative and sum are the same thing in some sense. That's why I call them both integrals. This is the subject of Theorem 2 from the article. Theorem 2. Suppose we have two operations, plus and multiplication. Such that multiplication is right distributive over plus. And suppose we have an operation triangle, such that the following property holds. A plus B triangle C equals to A triangle B triangle C. In group theory, this property is called associativity. Theorem 2 states that multiplication is right distributive over the triangle if, only if, let's write it down, A triangle B times C equals to AC triangle BC. This is the right distributivity. If and only if, triangle operation has a form A triangle B equals to I A plus DB, where D is a function that satisfies the chain rule. D AB equals to D A B plus dB. And I is inverse function of D. In group theory, this construction is called conjugation. Today we will prove only one direction, the backward one. And we don't need associativity for that. So let's write down once more what we have. Suppose the function D satisfies the chain rule. That is, D AB equals to D A B plus D B. And let the triangle operation is given by conjugation. A triangle B equals to I A plus dB, where I is the inverse of D. I'll talk more about inverse functions in the next video. For now, it's enough to understand that the functions D and I in some sense cancel each other. That is, for any A, I dA equals to A. And this is also equals to dIA. We want to check the distributivity of multiplication over the triangle. That is, A triangle B times C equals to AC triangle BC. For this, we need a lemma. It states that I has the following property. For any x and y, I x, I y equals to I x, I y plus y. Let's prove it. Okay, let's say that A is I of some x and B is I of some y. A equals to I of x and B equals to I of y. We can do it just because we want to. Now, let's substitute this into the chain rule for D. So here we substitute. Instead of A, we put I of x. So D, I of x. Instead of B, we put I of y. I of y. This equals to D of A, which is I of x. D of I of x. Here, instead of B, we put I of y. I of y. And plus D of B, which is I of y. I of y. And here we see that D cancels I by our cancellation rule here. So this is equal to x I of y plus y, because D cancels I here. And we see that these two parts are equal. But if two parts are equal, we can apply any function to them. For example, I. But here, I cancels D again by cancellation rule here. That is, we can write just what we have in brackets. So we have I of x times I of y. And we got the rule we wanted to prove. The lemma is proved. And we are almost done. Let's prove the implication in Theorem 2 using the lemma. Remember that we want to show the distributivity of multiplication over the triangle operation. We write the left-hand side using the definition of triangle, which is written right here. I A plus dB. And again, we use the fact that I cancels D to write C in the following form. I D C. I cancels D, and we got just C. Now apply the lemma, taking A plus dB as X and dC as Y. Let's write this in the following form. We write A plus dB instead of X here. A plus dB. Here we write I of Y. Y is dC. So we write I dC plus Y, which is dC again. Pause and check this is exactly the formula from the lemma. And as usual, I cancels D, so we can write just C. By ordinary distributivity of multiplication over plus here, we get I AC plus DBC plus DC. And here we see exactly the chain rule formula, same as here. So we simply get DBC here equals I AC plus DBC. And finally, by the definition of the triangle, we get AC triangle BC, which we wanted to prove. In the case of the antiderivative, we put the operation of multiplication of real-valued functions instead of plus, and the composition instead of multiplication. Then the conjugation becomes F triangle G equals to I F plus DG, or simply integral F dg. And the chain rule for the derivative turns into d f composition g equals to d f composition g times dg. This is the familiar chain rule. As a corollary of the theorem 2, we get the formula I already wrote above. Integral f dg composition h equals to integral f composition h dg composition h. This is exactly what is written here. Integrals of the real numbers work by the same laws, for example, summation, and each corresponds to its own function with a chain rule. For summation, this function is x minus 1. However, this is a topic for another video. That's all for now. Please like the video. Also, in the description you will find links to support my work, so I can continue my research and develop this channel. If things work out, I'll keep making videos about what I do and about mathematics in general. Thank you.